Hey everybody, welcome to my course on advanced probability. This is a thorough introduction to random variables that's suitable for advanced undergraduates or early graduate students. As a major goal of this course, I want you to be ready for professional grade study of statistics and machine learning. Coincidentally, the content of this course is very closely aligned with the actuarial P exam, the probability exam. So even though I'm not intentionally trying to make a prep class for that exam, if that's what you're here for, you're in the right place. Typically, students in this course have already completed an introductory statistics course, like the one I have, Normal Knowledge College Statistics. I'll throw a link to that up top. So if you're looking for something a little bit more introductory in terms of probability and statistics, I recommend starting there. There is a fair amount of math in this course. You should have a solid grounding in integral calculus, including improper integrals and integration by parts. It's not so much that you're going to need to do a lot of integrals on your own, but if you don't have these concepts at a pretty solid level, you're going to get lost very quickly. By and large, I'm going to use technology to do my integrals, but I want to stress the understanding and the ideas that goes along there. You'll also want to have comfort with mathematical proofs and algebraic techniques at an intermediate undergraduate level. This course is an opportunity to get better at both of those things, but if you've never seen mathematical proofs, haven't worked with slightly more involved algebraic techniques than you might have in a high school algebra class, this class might be a little bit more advanced than what you're looking for. Multivariable calculus is helpful. It's not required. There will be a few triple integrals, but I'll kind of cover them as we get to them. And again, you don't have to do any of this by hand. There are 5 major parts to this class, and in fact, to any probability class that you'll have at the advanced undergraduate level. I've listed them here. I want to run through each of them a little bit more in depth. First of all, we need to understand exactly what we mean when we use the word probability and consider some of the basic properties of probability. In the context of this course, we're going to understand probability as a function, and its domain is going to be subsets of the sample space, that is, events, and the range will be real numbers between 0 and 1. There are different ways of defining that function depending on the context, and so we'll have to get into some of those different ways. One quick example, suppose we have this unit disk in the sort of light blue here, and we're going to take a point at random. We could define the probability that the point lies in a specified region E to be the ratio of the area of the region E and the ratio of the overall disk. Since the area of the disk is pi, the probability that the point lies in E is the size of E, the area of E, divided by pi. If we know the probabilities of 2 events, then we can compute the probabilities of different combinations of those 2 events, including the intersection or union, that is the and the or of the 2 events. We can get the probability of the complement, and we can talk about conditional probability, the probability that one happens when we know that the other one does. By the way, we're going to go into that in substantially more depth and specificity than you'll see in an introductory statistics class like NK College Statistics. The big payoff for this part of the course is the formulation of Bayes' rule, which is really fundamental in all of statistics. It specifies how the probability of an event should be updated as new information comes in. Part 2 is going to be discrete random variables. By a random variable, I mean a random occurrence with a numerical outcome. When we start talking about random variables, we're immediately going to get into the concept of expectation. The expected value, the average value of the random variable, sort of what we expect its value to be if we do the thing many, many, many times. We're going to seek to understand it and learn to compute with it efficiently. Expected value is fundamental to some other really important concepts in probability theory, including variance, or spread of a random variable, related standard deviation, as well as skewness and kurtosis, which we'll define and get into as the course goes on. We also need to get into the moment generating function, which is a bit more abstract, hugely powerful tool in probability theory. With those tools in mind, we'll be ready to understand any random variable that might come our way. In particular, we're going to talk about some of the most important discrete random variables in the real world, including the binomial distribution, hypergeometric, negative binomial, and Poisson distributions. By the end of this section, you'll be able to model occurrences of unpredictable events like accidents on a highway, cases of an infectious disease, or flaws in a production process. The next part of the course is continuous random variables. Probabilities are harder to describe when you have a continuous random variable. For instance, if you're talking about the duration of calls to a customer service line, it's not really appropriate to ask the probability that the call lasts exactly 150 seconds. That probability is going to be essentially zero. The actual call length is probably 150.1 or 150.01 or one of another uncountably many values nearby 150. And this leads us to consider probability density, which is used in probability computations in much the same way as physical density is used in calculations of mass, which is to say, we're doing integrals. Many concepts in discrete random variables carry over to the continuous case. So we'll again talk about expected value, moment generating function, standard deviation, variance, all that good stuff. Then we'll get into some of the most important probability distributions for continuous random variables. The good old normal distribution, the t-distribution that stands in for the normal distribution when the standard deviation is known, as well as the gamma and chi-squared distributions. After that, we'll want to talk about distributions where we have more than one random variable, so-called bivariate distributions. Everything gets more complicated in this situation. For instance, suppose we're just rolling two dice, and we're letting x be the number shown on the first die, and y the sum of both of those dice. We have to come up with some more specific ideas of what we mean by expected value and variance now. Those can mean lots of different things here. Notice in particular that if we know the value of x, that gives us information about the value of y. So these two variables are not going to be independent of one another. We'll also need to define independence, by the way. Some of the core concepts that we'll cover in this part of the course: joint, marginal, and conditional expectation, also variance and so on. We'll talk about covariance, and we'll talk about the correlation of random variables. For each of these concepts, we'll have to think about the discrete and continuous cases, although they end up being fairly similar in our computations. Finally, we're going to talk about functions of random variables. We're in a situation where we know the distribution of a random variable x, and we have some mapping f that's going to take x and map it to a new random variable y. So what can we say about that distribution? For instance, we're going to show that if you have a random variable with a standard normal distribution, and you look at its square, then that new random variable is going to have the distribution chi-squared of 1, a chi-squared distribution with 1 degree of freedom. Very important in this part of the class is the notion of a sample, which is a collection of independent and identically distributed observations. So basically you have one distribution, and you're just taking a lot of observations from it. When considering functions of more than one random variable, we're going to stick to this case because it's by far the most common and important in the real world. Here's the reason why. A statistic is a number that's computed from a random sample. Viewed a bit more mathematically, a statistic is a function of a collection of identically distributed independent observations, x1 up to xn. The two most important statistics that you'll see are the sample mean, x bar, which is the sum of all the xi's, all the observations you've made, divided by the number of observations, and the sample variance, which is 1 over n minus 1 times the sum, xi minus x bar quantity squared. And both of those statistics you're probably familiar with from previous courses. By ending with statistical sampling, this probability course segues directly into that professional grade study of statistics and machine learning that I mentioned earlier. If you're taking a course like this at a college or university, typically you follow it up directly with a course with a title like Mathematical Statistics or Statistical Inference. You'll be ready for any course like that. Finally, just a quick comment about how to use this course. On the one hand, you can absolutely learn the general ideas of this material with a casual viewing and get a lot out of that, especially if you don't multitask while you're watching the vids. On the other hand, if you're hoping for a level of knowledge that's going to let you compete in the data science job market, if you want to do something a little bit more technical, a little bit more statistical or mathematical, you're going to need to practice doing this stuff by yourself. You need to actually work on those skills a bit more intentionally. Throughout the course, I show practice problems and then pause where you can stop the video and try the problems on your own before continuing with my solutions. And if you're in a situation where you're trying to compete on that job market, I strongly recommend that you do practice those problems on your own before seeing how I work them out.